So thank you, Daniel. Yes, this was a great setup for what I wanted to talk about. So perfect stuff. So I wanted to talk about basically proofs in machine learning. Yeah, so let's dive right in. So I didn't quite know what the audience background is going to be, so I figured I'll just do a very quick overview of snarks. Maybe many of you already know what it is, but it doesn't hurt to kind of make sure everybody is on the same page. So what is a snark? A snark basically is a succinct, non-interactive, well, it stands for succinct, non-interactive argument of knowledge, but really it's just a proof, a short proof that something is true, yeah, that a statement is true. Yeah, for example, I can prove to you that I know a message M that happens to a hash to 0, and a snark would let us produce a very short proof of this fact. Yeah, so what a snark would do is, first of all, it's a short proof, and second of all, it's really fast to verify. Yeah, and the thing I want you to take away from this slide is that the trivial proof, where I just send you the message M, yeah, is neither short nor fast. If my message is a gigabyte long, that's a pretty large proof that I know something that hashes to 0, and it also now you have to hash a gigabyte of data, which could take a while, so it's not short and it's not fast to verify. It's kind of remarkable that a snark lets us prove that I know a gigabyte message just using a couple of hundreds of bytes, and it only takes a few milliseconds to verify that the proof is correct. It sounds kind of impossible, and yet with the magic of cryptography, we can actually do this. I remember, maybe some of you have heard me say this before. I gave this talk a while ago to, and there were some political scientists in the room. So they asked me, great, can you give us a snark proof that Biden won the 2020 election? And I said, no, that's not the sort of things we can prove. These have to be mathematical statements. Yeah, like, SHA of a message is equal to 0. All right, there's also a ZK variant of snarks where the proof also reveals nothing about the message M. So just going through this very quickly, I just wanted to make sure we're on the same page. So snark systems have to have a couple of properties. I just wanted to make sure everybody's familiar with these words. So complete means that an honest prover will always convince an honest verifier. Sound means that a dishonest prover cannot fool the verifier into accepting a false statement. Succinct means what I just said before, that the proof is short and is fast to verify. And zero knowledge, again, means the proof reveals nothing other than the validity of the statement. Okay, so just a very quick informal description of what the properties are. There is a huge industry around these snarks. It's really, I can't believe I'm not living in a dream. 20 years ago, this was a very theoretical topic. Now, all of a sudden, there's like multi-billion-dollar companies working on improving snarks. So again, many of you know this. I mean, there are people building hardware. There are people doing whole companies just doing audits of snark systems. There are people building proof systems, including Nexus and many others. So the reason this is so successful is, again, there's been a lot of improvements in snark systems. Now they run really fast. Lots of beautiful ideas. Lots of commercial applications. Maybe I just saw a number that I thought was interesting last night. This is from Matter Labs. They just announced this in East Denver. They say that on their prover, they can do this on an H200, a single GPU. They can prove 30 million RISC-V instructions per second. That's a pretty impressive number. 30 million instructions per second on one GPU. That's kind of cool. Okay, so from this point onwards, I could take the talk in two different ways. I could kind of tell you how snarks work under the hood, and this is an area that I love to work in. We have a bunch of results that I would have loved to tell you about, but that's not what I'm going to talk about. Instead, we're going to talk about applications, and in particular, I want to talk about applications to machine learning. Okay, so that's what we'll now flip gears and talk about that. All right, so let's talk about snarks in machine learning. So this area goes under the heading of ZKML, ZK for machine learning. And the example that I like to give is this idea of a bank that trains a model to do a certain task. Yeah, so maybe the bank basically trains a model to decide whether I should get a mortgage or not. So the way this works is, the model trains this, the bank trains this model. Theta is the model here. Now Alice comes along and says, here's my financial data. And the bank says, okay, great, I ran the model and the model rejected your application, right? So Alice is now wondering, wait a minute, this is kind of unfair. How do I know that the same model is used for everyone? Maybe you used a bad model for me and you're using a different model for everybody else. And how do I even know that the server ran the model correctly? Yeah, this seems kind of an unfair state of mind. And so what we would like to do is we would like to have the server, actually the bank, actually commit to this model. And the commitment is really short. The commitment can be published to the whole world. The commitment reveals nothing about the actual model itself. It's kind of important to keep the model secret. Yeah, this is maybe has not been said enough today. It's kind of important to keep the model secret, because if you don't keep the model secret, it's quite easy to come up with adversarial examples where the model makes mistakes. Okay? Sometimes it's possible to do it even when the model is secret, but definitely it's not a good idea to publish these kind of models. Yeah, so instead of publishing the model, the server just publishes a commitment to the model. The commitment reveals nothing at all about how the model works. Yeah, and now what the server can do is it can attach a proof to say, yes, this result that you got for your loan application, A, was done using the model that the server committed to. Yeah, so the model was computed correctly, and it was computed correctly relative to this public commitment. So now you are guaranteed that the same model that was used to analyze your application is used to analyze everybody else's application. Does that make sense? That's kind of the premise of ZKML. But if you have an adversarial mindset, you realize, wait a minute, this doesn't prove anything. Right? The fact that the same model is used for everyone doesn't help at all, because the first line in the model could say, if applicant equals Dan, say no, else run the model. Right? So that model would not be a fair model. And so that's kind of the first thing that we looked at. Oh yeah, sorry. Before I go there, the question is basically, is this really practical? Can you do this in practice? And so I'll tell you that there's a commercial system, it's called Ezekiel, EZKL, that actually generates ZKML proofs for lots of different architectures, for PyTorch, Random Forest, SVM. Very interesting commercial model that's actually deployed and used like all the time today. Okay, so the question is, the fact that the same model is used for everyone is not enough. We have to prove the model is actually fair. And so that's the next thing we looked at, basically. So we have a system called FairProof, that basically what it does is not only does it produce a proof that the right model ran on your financial data, it also produces a proof that the model satisfies a certain notion of fairness. This is a notion of fairness that comes from the algorithmic fairness community. It's called local individual fairness, which means that similar people are treated similarly. So for example, it's not the case that the model says, if name equals Dan, say no, else run a model, because that would not be fair, because someone similar to me would be treated very differently from how I'm treated. So the way local individual fairness works is you take my financial data, you put a bubble around it, you put a sphere around it, and you want to argue that all the points in the sphere are treated roughly the same. So most of the points in the sphere the model will respond in the same way. So that's what this proof system actually does. It proves that not only was the correct model applied, this model actually doesn't depend on gender or zip code, or it doesn't depend on any of the protected characteristics that we're not allowed to discriminate relative to. Okay, so the question then was, how do we design an efficient proof system for proving model fairness? And that's kind of what this system does. So this was actually a lot of fun to develop. You want to optimize the proof system so you can generate these proofs at a reasonable speed. I can tell you we tried 3 different models. This is an income predictor model, this is a loan application risk model, and this is a likelihood to default model. And for all of these models, you can see we can generate these proofs of fairness in just a few minutes, like under 6 minutes for all these models. So I don't know, maybe this was basically on our laptops. You know, if somebody has a good cluster, probably this will go a lot faster. But the point is, you submit your application, the bank will generate a proof, and what comes back is a proof that A, the same model that was used for everyone was used for you, and this model does not discriminate based on gender or other protected characteristics. Make sense? So that's kind of a nice application of ZK for the real world. But we didn't stop there. The next thing that happens is when the model rejects your application, there's often a legal requirement that you have to provide an explanation. Why was my application rejected? Yeah. And so the question is, how do we provide these explanations for why was my loan application rejected? And there's actually actually here, I'll tell you the way we would like to do that is we send the decision back, we send the explanation back, and we send back a proof that the explanation was computed correctly. I can tell you the way explanations are typically computed is using an algorithm called LIME. LIME is a very simple idea. I can explain it in 2 seconds. Basically, when I take your financial data and I treat it as one point in space, then what we do is we sample the model around your point in space, and we approximate a linear model around that point. Okay, so of course the model theta is a very complicated model. It's defines a very complicated shape, but locally everything looks linear. So around your financial data, your point in space, we train just a linear model that approximates the complicated model. And this linear model basically is just a linear, it's just a, it's an inner product between your record and a bunch of weights. And so the linear model, when it assigns a high weight to a particular attribute, that says that that attribute was important in making the decision. Okay, so the linear model really is an explanation for why the model rejected or accepted your application, because it tells you which attributes played an important role in the decision. Okay, and so what we can do is we can basically generate this proof that the LIME algorithm ran correctly. And not only is the model the same model that's used for everyone, it's guaranteed to run correctly, but now you're also guaranteed that the explanation you get back for why your application was accepted or rejected is also consistent with the computed model. Yeah, so again, this is all implemented. It runs in here. It runs in about a minute and a half to generate these proofs. This was implemented as an extension of Ezekiel. So anyone who's using Ezekiel to generate ZKML proof can now also generate proofs of explanation. All right, so that was the first thing I wanted to walk through, basically verifiability of fairness and explanation using SNAR techniques. Yeah, so please use this. I mean, this is like meant for everybody to use. Yeah, so everything is open source and available for anybody to use. Seems kind of a useful thing to provide. Cool. So now let's switch gears, and I want to talk about a different thing. And I guess I have 5 minutes left, so I can do this, I think, in 5 minutes. So the next thing I wanted to talk about is, I guess Jens and Daniel talked about how to do verifiable inference. The other part of machine learning is verifiable training, right? I mean, you train and then you do inference. The problem with training is it's a massively expensive compute process, right? Much, much harder than inference. So the question is, unless you are like Google or OpenAI or Facebook, you can't train models yourself, right? You have to go to the cloud and say, I need to train a model. Hey, can you help me? And then so what you have to do is, you go to somebody else. You say, please help me train this model. You send them the training data, and they send you back the model. Now, the problem is, well, who is this person that trained this model for me? Can I really trust this model? And again, the issue is that there are lots of ways in which a trainer can cause harm. For example, they can undertrain your model. You can run for fewer steps that are necessary. They can modify the training data. Yeah, so that they don't train on your full training data. And the worst thing they can do is actually they can train the model correctly on your training data, but they actually embed a backdoor in your model so that the model will behave correctly on all the test data, but there will be like one secret input when the model makes a completely wrong decision. Yeah, so that's actually quite scary. I don't know, if we're training a model to drive a car, then the model will be perfectly fine unless this one particular thing happens, and then, I don't know, something bad happens. Yeah, so how do we avoid these backdoors? This is kind of a big deal. There are plenty of papers that show that it's actually not that difficult to embed backdoors in trained models. So what do we do? So how do we do verifiable training? So there are really 3 approaches, right? We only know how to do verification in 3 different ways. So the first way is we do, let's take the ZK approach. Yeah, let's just prove that the training algorithm ran correctly. So there are papers that are trying to do that. That turns out mostly works for relatively simple models. Yeah, for complicated models with over 1 billion parameters, probably the ZKML approach is still too hard to do. It takes too long to generate this proof. Okay, so that's a little bit too hard. The second approach is, if we want to do verifiable training, the second approach is let's train inside of a trusted execution environment. And Ilya talked about that. Yeah, that's exactly what he was saying, and that works. You can totally train inside of a TE. The H100s. In fact, this whole line of processors from NVIDIA supports TEs, so we can train inside of a TE, and the trusted execution environment will sign the fact that it ran the model correctly. So that works. But now you're at the mercy of the hardware vendor, right? So if for some reason there's a hardware attack, maybe there's a supply chain attack, then things could go wrong. We'd like to do something, we'd like to have other options. The third option, let's see, I wonder if anybody can yell it out. The third option for doing verifiability is what? So ZK was one option. TEs is another option. What's a third option for doing verifiability? Thank you. Yes, optimistic. Exactly. So we could try to use fraud proofs to do verifiable training. So this is exactly applying a blockchain technique to machine learning using the optimistic approaches were first deployed in the blockchain. Okay, so the idea is this: you send your training data to the trainer sends you back a model, and then you say, great, this is my model. Can someone verify that my model is correct? So an auditor stands up and says, sure, I'll verify your model for you. You send them the training data and the model, and they rerun the training, and they say, oh, this is a good model or this is a bad model. If they say it's a bad model, they run through what's called a fraud-proof game to prove that actually they were correct and the trainer was lying. Okay, so that's kind of the idea. So I thought, great, we could just do that and problem solved. Unfortunately, this doesn't work. Yeah, this is, I don't know, this is a little bit of a surprise to me. This doesn't work. So why doesn't it work? Let me explain. The problem is this. The trainer might be using an NVIDIA H100. The auditor might be using an NVIDIA A100. And even though they're both computing exactly the same algorithm on exactly the same data, these GPUs are crazy. They are not deterministic. Yeah? So you can try to do A plus B plus C or A plus B plus C, and you get different answers. Yeah, it's because of what? Because of floating points. Yeah, all evil in the world goes back to IEEE floating points. Yeah, so it's because of floating points that you get close answers, but they're not exactly the same. And training is such a CPU-intensive operation that even minor errors very, very quickly kind of cause complete divergence in the training data. So you can try to send your in the model that's generated. So you can try to send your training data to both, but they'll end up with completely different models. It's really quite remarkable. I mean, these models are both equally effective. They have the same accuracy, but they are completely different from one another. So auditing just doesn't work on the face of it. Yeah, so you end up with completely different models, and it's basically because of what I said. So maybe I'll show you actually the graph. This is really interesting. So here's a graph that as you run it for more and more iterations, you literally see the auditor and the trainer diverge. You can see that the L2 distance between the weights of the models, as you run it for more and more iterations, they just become like, a third of the weights become completely different. Yeah, so they just completely diverge. The green line, by the way, is our method, which shows that we can keep them together. So I can tell you what we do is basically we try to kind of work hard to identify what are the sources of non-determinism. And then every time the trainer makes a computation that looks like it introduces non-determinism, it actually records the decision that it made. Yeah, so it records kind of all these non-deterministic points, sends them to the auditor, and then the auditor can kind of fix its non-deterministic choices to match exactly what the auditor did. So the most we can train ourselves is GPT-2. So we ran a GPT-2 training procedure. With GPT-2, we have to record about a couple of megabytes of data. Yeah, and using that couple of megabytes of data, we can basically make sure that the trainer and the auditor end up with exactly the same model. So you can see actually there's literally no difference between what the auditor is getting and what the trainer is getting. Yeah, that's kind of the idea of verifiable training using optimistic approaches. So we have these three approaches. TEs are fine. If you like TEs, it's a perfectly fine way to do it. We also like optimistic methods, and this is a way to make optimistic methods work. Cool. So I think I'll conclude here. Basically, to me, this is amazing times. Yeah, I mean, it's really kind of cool to see the succinct proofs they're having so much practical applications, and there's so much effort behind making them real. So I like to say that, I don't think we say this enough, but I think it's really important to say this over and over again, that the reason succinct proofs became real is because of the blockchain world, but now the rest of society can benefit from it. Yeah, so we can use it for ZKML. We have some other work that shows how to use it to fight disinformation. So we're finding all sorts of applications that have nothing to do with blockchains, but those are possible only because of blockchains. Yeah, I think we should say this. This is kind of a good contribution to society. And finally, as I say, machine learning turns out to be a really cool playground for lots of cryptographic techniques. So there's infinite work to do. So yeah, please get involved. And I'll stop here. Thank you very much.